Good afternoon. Let's get started. Let me begin with a couple of announcements. We have a conference, two-day conference starting at UT tomorrow and Saturday. The theme of the conference is The Next Oil Crisis. Is the boom just another bubble? Location for the conference is the Etter Harbin Alumni Center, and it starts at 8 a.m. tomorrow morning. So if you have some time and interest, please join this. There are some very extraordinary speakers and panels lined up there. For next week, we do not have a lecture or a speaker, but it's a very special event at the Symposium next Thursday. We will have energy vignettes. This is a 10-video clip series that the students in the Energy Symposium has developed over the course of this semester. So please join us next week to see these very, very interesting, innovative, thought-provoking videos on a range of energy issues. We have saved the best speaker for the last. It gives me tremendous pleasure to introduce my distinguished colleague, Dr. Dale Klein. His career, both intellectually in the academic arena as well as in public service, has been so distinguished. Anything I say will not do full justice to that, but I'll still introduce him briefly just for those of you who may not know him. At UT, he is the Associate Director of the Energy Institute, the Associate Vice President for Research, and a Professor in Mechanical Engineering. He is also the Associate Vice Chancellor for Research for the entire UT system. He was appointed Chairman of the Nuclear Regulatory Commission by President George W. Bush and served in that position from July 2006 to May 2009. Before joining NRC, he was Assistant to the Secretary of Defense for the Nuclear, Chemicals, and Biological Defense Programs. And he has held several other very senior positions. I was talking to him a few minutes ago, and he is now the chair of the Reforms Committee for the TEPCO in Japan, and he'll probably touch upon some of those issues. He has authored over 100 technical papers and has given 400 very high-level talks at a wide variety of national and international venues. And he holds a doctorate in nuclear engineering from the University of Missouri, Columbia. He will talk to us on the road forward for nuclear in the U.S. and internationally. Please join me in welcoming Dave.
Well, thanks, Varun. It's always fun to talk about my favorite subject is nuclear stuff. And so what I'll do is give a little bit of a background, and then the best part is the Q&A period. Normally, I pace back and forth so that I'll always give the people filming a challenge, but since I have to push the buttons, I'll stay close. One of the things that I always have to make sure is that being nuclear trained, I don't push buttons unless I know what they do. So I had to get some training on this one. What I'd like to do tonight is basically talk a little bit about, give you some basic background on how nuclear plants work, what the issues are. Then we'll talk a little bit about the world nuclear situation. The world is clearly going to go nuclear. It's not clear what the future will be for new plants in the U.S., and I'll talk a little bit about why that is the case. And then obviously Fukushima is something that I think a lot of people have an interest in. And as Varun indicated, I was asked to chair a reform committee. The hierarchical structure in Japan makes nuclear safety a different cultural issue than it does in other countries, where typically information comes top down instead of bottom up. Japan has done a very, very good job in the area of manufacturing, where any worker can stop the plant if there's a perceived defect in the product. That same system of culture does not exist in nuclear safety. And so I'll talk about why some of their problems had occurred. It's really stark when you go to the Fukushima Daiichi plant. A lot of people don't realize it, but there's Fukushima Daini, which is about 10 kilometers from Fukushima Daiichi. So there's two different nuclear sites very close together. At the Daini plant, all four were running. And that particular unit maintained one off-site power, so they were able to eventually shut those down safely. Daiichi, they lost everything, and I'll walk through that sequence. And so that's why you had two close together One had a very serious problem. The other ended up being shut down safely. And then the fun part is the Q&A part. So how many of you have had physics? How many of you have heard of physics? Just checking to see if you're awake. The thing that really makes nuclear different than other forms of energy is you're dealing with the nucleus of an atom as opposed to the weak electron clouds. So what you do is you go out and you find your friendly atom, in this case uranium-235. If that atom is hit with a neutron, it becomes unstable and splits into two parts. Have you ever heard of this equation called E equals mc squared? So you're basically taking mass and converting it into energy. That energy then, when you release the fission fragments, you have some extra neutrons left over. They will create other fissions, and so you can create a self-sustaining chain reaction. And so it's a very compact form of energy. And if you look at a number you can write on your hand and impress your friends at cocktail parties, if you create a CO2 molecule, so if you burn something, you create CO2. So when you make CO2, you get 2 electron volts. Now, you don't have to know what an electron volt is. It's a unit of energy. If you split an atom of uranium, you get 200 mega electron volts. So you get 100 million times the amount of energy when you split an atom dealing with the strong nuclear forces as opposed to the weaker electron forces when you burn stuff. So what that says, if you want X amount of energy, then you have to burn a lot more things than by splitting atoms. And so that's why that little fuel pellet that's about a ½ inch in diameter, ½ inch long, will have the energy equivalent of a ton of coal. So a very compact form of energy. I was giving a talk in Dallas a number of years ago to a high school science class, and that little pellet is also equal to 50 gallons of gasoline in energy equivalent. So this student held up his hand and said, "Do you mean if I put that little pellet in my car, I can go for a long distance?" No, it doesn't work that way. It's an energy equivalent. It doesn't really work the same way. So what you do in a nuclear plant is you take those little pellets that as you make fissions, the pellet gets hot, you have them in a long rod, and so you flow water by that rod, so the rod gets hot, and all a nuclear plant does is boils water. Just makes a lot of hot water. And so you'll see the pellet goes into a fuel rod that goes into a fuel assembly. Those assemblies then go into a big vessel. And what happens in a case like, in this case, for a pressurized water reactor, you'll end up having the water that will flow by that reactor bundle. It gets hot. It goes through what's called a steam generator, where you'll take the liquid water, turn it into steam. That steam then goes through a turbine, like a pinwheel. When the steam hits it, it turns a shaft. That turns a generator, and that's how your magic electricity comes out. So when you look at a typical fossil fuel plant, whether it's oil, coal, or gas, you typically will have a lot of the similar characteristics unless it's a gas turbine. But for a gas steam plant, you're still turning steam, water into steam, runs a turbine. And so in the case of a pressurized water reactor, in the vessel itself, it always stays liquid. It's under high pressure, so that water is always in a liquid form. In another reactor, obviously called a boiling water reactor, inside that vessel at the top, it goes from liquid to steam, and then that steam will then go through the turbine. It's condensed and comes back into the reactor. So both of them have closed loops, but in the boiling water reactor, you actually make the steam at the top of the vessel that goes into the turbine. The kinds of reactors that occurred at the accident at Fukushima Daiichi were boiling water reactors. Both are safe. I used to say it's like, would you rather have a Ford or a Chevrolet? With the high cost of construction of these reactors now, it's more like a Mercedes or a BMW. So it sort of depends on your preference, but both are safe. They're just slightly different. If you look at the world situation, one of the reasons that people have nuclear power plants, one key point is energy diversity. I don't care what form of energy you have, it's not perfect. If there were a perfect form of energy, we wouldn't be having energy debates. And so basically, you don't want all your eggs in any one basket, so you want a diversity because you don't know what the future will hold. The other advantage of nuclear, it is sustainable. There's a lot of uranium around, and if the uranium price gets high enough, then you can go to a breeder reactor, and you can convert uranium-238 to plutonium-239, and you can actually make more fuel than you consume. So in a breeder reactor, if you have a 1,000 megawatt electric plant and you put the fuel in there, it will generate enough fuel for itself plus 3 other reactors. So breeder reactors can go for centuries. In fact, if you look at the weapons program, there's enough depleted uranium at Oak Ridge National Laboratory and also at some sites in Kentucky and some in Tennessee, that there's enough uranium that would supply all of our electrical needs in the United States if all were generated by nuclear for 700 years, if you put that in a breeder reactor. So it is definitely a sustainable form of energy. A lot of countries look at nuclear for economic reasons. Now, it turns out that's not the case now for the United States. But I serve on a nuclear safety board in the United Arab Emirates. Probably you realize United Arab Emirates has a lot of oil, but they're building 4 nuclear reactors in Abu Dhabi. And the reason they're doing that is they can basically generate their electricity from nuclear cheaper than they can use it from their oil. They can sell the oil, and so it's an economic advantage for them to sell their oil and generate electricity from nuclear. In the United States, while I was chairman of the Nuclear Regulatory Commission, we had 19 applications for 28 reactors. Almost all of those had gotten either deferred or put on hold. And a lot of people think that it was due to Fukushima, but it had nothing to do with Fukushima. It's called cheap natural gas. You know, fracking is really a game changer. It has changed our whole energy picture. And so if you talk to a company like Exelon that's a merchant plant, they tend to be in merchant economies in various states. In order for nuclear to compete on an economic scale, they want $8 a 1,000 cubic feet gas, and they want a $25 ton carbon tax. So under those economic conditions, it's worth their risk to build a nuclear plant and then bid into a market. Obviously, with gas running below $3 a 1,000 cubic feet, the economics just don't work right now for things like nuclear that are very capital intensive. But if you go to other countries where the price of natural gas is still tied to the price of oil, and that's almost entirely true in all the Asian countries. So when the price of oil goes up, the price of natural gas goes right up with it. And so the last time I was in Japan, they were still paying about $14 a 1,000 cubic feet for natural gas. And so under those conditions, nuclear is definitely economically competitive, but not in the U.S. The other thing is the world energy increases. We're going to need more and more electricity. And so as you look at the demand and you want to diversify, that's why nuclear worldwide will continue to grow because of the increased electrical demand. I was in India a few years ago, and I was surprised to learn that 60% of the population in India does not have electricity. And you think of the population of India, if they're going to get their economic society elevated, they're going to have electricity. And they can't do it just on fossil fuels alone. And so they have a very expanding nuclear program. So if you look at the world situation for reactors today, there are about 435 around the world. The United States has more reactors than any other country. You hear a lot about France. France gets 80% of their electricity from nuclear. But the United States has more reactors. They just have a higher percentage. And so usually when you think of France, there's 4 reasons that they get 80% of their electricity from nuclear. Do you know what those 4 reasons are? Any guesses? They don't have much, so they have, the 4 reasons are no oil, no coal, no gas, no choice. So their situation, if they want to be energy independent, they had really had little option. And so they made a policy decision as a country to move into the nuclear world. It was with U.S. technology, but they've done very good at developing that within their country. When you have only one utility company that's government owned and one reactor vendor that's government owned, you can standardize and you can sort of drive your policies in a much different way. So if you look at the reactors under construction, there are about 63 reactors under construction around the world. China is the gorilla in terms of new construction in the world. They have 26 reactors under construction, a massive program. They're also bringing on about 1,000 megawatt coal-fired plant every week. So the demand for electricity in China is huge. And you think about the pollution that coal will result in, it's good to have a diversified program. Russia is second at 10, India at 6, UAE has 4. United States has 4 new plants under construction, 2 in the state of Georgia by the Southern Company, and 2 in the state of South Carolina by SCANA. And then TVA is finishing a plant called Watts Bar 2 that had been stopped. It was about 85% complete when they stopped construction, and so they're finishing it. So the U.S. really has 5 plants underway. So if you want to go out to your friendly vendor and you want to buy a reactor to put in your backyard, it'd be nice to know what your choices are. So there are really about 5 choices that we have today for reactors. There's the economic simplified boiling water reactor that General Electric has, the ESBWR. And then in the middle right, the AP1000 is Westinghouse. Both the AP1000 and ESBWR are passively safe designs. So in the 90s, the industry looked at what can they do to make reactors simpler and safer. And so General Electric did a design for their boiling water reactor. Westinghouse did their design for the pressurized water reactor. And both of those reactors are simpler and safer. And so as a recovering regulator, as Varun indicated, I was chairman of the Nuclear Regulatory Commission. So as a recovering regulator, if you have something that is simpler and safer, that is good for the industry, it's good for the American people, and it's good for the industry as a whole. So both of those reactors are what we call the new generation. There are other reactors that are under consideration. Mitsubishi Heavy Industry makes the US APWR. There are 2 sites that we're considering that design. Have any of you heard of Comanche Peak? How many have heard of Dallas-Fort Worth? Just checking. So Comanche Peak is near Dallas-Fort Worth. South Texas is obviously in South Texas near Houston. And so at Comanche Peak, they were looking at MHI as their design. But if you look at what Westinghouse was very clever, if you look at this map, you'll notice that the AP1000s were all in the southeastern part of the United States. The thing that's interesting about that part of the world, as in the U.S., is that it's still regulated and the growth rate was pretty high. So they had targeted that part of the country where they wanted to focus their attention. And that's where the 4 reactors of the AP1000 are being built in the southeast. The rest of the country, for the most part, are merchant plants where a utility would have to invest several $billion and then they'd have to bid in on what the market would be. So if the price of gas is high, they're good to go. Price of gas is low, they could lose the company. The EPWR is it used to stand for the European pressurized reactor, and it's the French version of the pressurized water reactor. And so it's called it was a change from European to enhanced pressurized water reactor, so they could still keep the E word but not have the stand for Europe, since they wanted to market it worldwide. So there are that reactor is being built in Finland, and then they're building 1 in France, and they're building 2 in China. So those are under active construction as well. So if you look at what's different about the nuclear industry today versus 70s and 80s, it was a very turbulent time for the nuclear industry. It was when changing regulations were occurring. In the late 70s, you had double-digit inflation, you had double-digit interest. That caused an exponential on your cost of capital-intensive equipment. So what's different today is that during the early 90s, again, the industry looked at what could they do to make things more predictable with no compromise on safety. And they changed the process from a 2-step where a utility would have to come in and get a construction permit. And then after they spent several $1 billion, they would have to come back to the Nuclear Regulatory Commission for Mother May I and say, after I have spent $5 billion, may I now operate it? That made companies a little bit nervous. When you think about delays, and a lot of those were legal delays, just calculate the daily interest on $5 billion at 5% interest, and you'll find out that that is a fairly large number. And so if you look at some of these delays that were tied up in the courts for up to 4 years, that is a huge amount of money that companies would have at risk. So what the industry and the regulator, the NRC, looked at was changing the process, no compromise on safety, where they would do a combined construction and operating license, the COL. So what they do is a company will have to get a design certified by the NRC. So in the case of the AP1000, Westinghouse came in with their design. The regulator went through all those designs, a lot of questions, and then they basically certify that design. Then during the construction, the NRC will inspect it to make sure it's built as they said they will build it, and they will do tests along the way. And then assuming everything is satisfied by the regulator, then they can operate it. Much like we do that for airplanes. You don't license every single airplane. You do an airplane design, you certify it, then you manufacture them according to specifications, and then you can fly them. The other thing that happened in terms of the industry, most of the 28 plants that were under consideration were at brownfield sites. So in the case of Comanche Peak, that site was originally designed for 4 reactors. They only built 2. South Texas, they built 2. It was again designed for 4. At the Vogtle site in the state of Georgia, where they're building 2 more, it was designed for 4. They only built 2. So most of the new reactors that were under consideration were at existing sites where these plants had been running typically for decades. So the public comfort level was much higher. You would have still opposition, but for the most part, the favorable factor was in the 75 to 85% because the people were comfortable with it. The plant had been there for a long time. The people that ran the plants went to schools, churches. They were basically parts of the community. And so it was not an unknown. So those were the 2 characteristics that really happened: improved licensing and then at existing sites. The other thing that occurred is that the Nuclear Regulatory Commission did a process where you could do an early site permit. So you could basically bound the parameters where you look at the characteristics of the plant, what the environmental impact is, and you can get a site pre-approved, and you could hold that for as long as 20 years. And then when you decide to build a plant, then you can actually do the fine details of exactly how does that plant operate on that site. And so that tells you that you can do like 90% of the permitting up front with one of the standardized designs, that the designs have already been certified. So the NRC has certified the advanced boiling water reactor. They have certified the AP1000. They're going through the process of certifying the EPR and the US EPR. So they're going through those design certs. Let me talk a little bit about safety. In terms of nuclear safety, what you typically look at is a defense in depth concept. You want to have multiple backups. And so if something fails, you have another system that will kick in and take over. If you need a diesel generator, then you'll put 2 of them in case one doesn't start. So you'll have a lot of defense in depth. The other thing that the nuclear industry does that is somewhat unique is that they invent an accident. And they say, we don't expect this accident to occur, but if it occurs, we want to contain all that radioactive material and shut the system down safely. And so typically that was called a double-ended pipe break, where you'd have a 30-inch pipe. The thickness of the pipe was about 2 inches thick. You assume that for whatever reason that pipe would move apart, water would come out of both ends, and then you would design your system to contain that release of pressure and the radioactive material. So that's why you'll see these big containment domes around reactors, so that you can contain that material. So that was a design basis accident. If you look at the car industry, what typically you'll put in enhanced safety features like seat belts, glass, safety glass, things of that nature. But if it goes beyond that parameter, that's just the way it goes. It's not designed to withstand necessarily a 70-mile-per-hour crash. And so they don't design those in a robust way. The other thing that most countries have independent regulators, and the NRC is an independent regulator. It is not a part of the executive branch. So when I was chairman, I had oversight by Congress, but I was not considered executive branch appointment. I was a presidential appointment, but I did not report to the president per se, because once you're confirmed by the Senate, then the commissioners are in there for the duration of that appointment. So independent regulators is a very important consideration, so that there's a check and balance on behalf of the public. The tagline the NRC had was protecting people and the environment. So that was sort of our tagline that we would have to tell people what we did as a regulator. The other thing that's very important in the nuclear industry is training. After 3 Mile Island, the utilities realized that as an industry, they're only as strong as the weakest link. And so they realized that even though only one utility had the problem at 3 Mile Island, it impacted everybody. So after 3 Mile Island, the Institute of Nuclear Power Operations got together and they strive for excellence. As a regulator, we had requirements that industry had to meet, but it's the industry's job to strive for excellence. And so that was a big difference in how they check each other as opposed to just the government regulator. After Chernobyl, there was the World Association of Nuclear Operators, WANO, that was formed to look at the same concept worldwide. INPO is basically a U.S. activity. And then the other thing that occurs in the nuclear industry for safety is practice. You do drills, you do exercises, you do systems, you do emergency evacuation drills, you do all of these planning and exercises. And so about once a month, I would go into the emergency operations office at the NRC and would conduct an exercise. And so we would invent an accident. The utilities knew it was coming, so it wasn't a total surprise. And so we wanted to make sure they knew how to respond. And so we would do terrorist activities. We would say, okay, your diesel generators are not going to start. So we didn't have to justify our assumptions. We said, these are the assumptions, deal with it. It's sort of like that ship in the desert. You know, you don't worry about how it got there, you just have to deal with it. So as a regulator, you can do that to those licensees. When I was a director of our nuclear program here at Texas, we have a research reactor at the Pickle campus, and it used to be in Taylor Hall, right in the middle of campus. And I was licensed by the NRC, and I can tell you it's a lot more fun being the regulator than the regulatee, so it depends on which side of the desk you sit on. When you look at the nuclear safety, and you look at all of those defense in depth, design-based accident, all of those sort of things, almost every one of those failed at Fukushima. Almost everyone, and I'll go through and talk a little bit about what happened. So I'm going to show you this picture now. This is the Fukushima Daiichi site. They had 6 reactors at the site. Only 3 were running when they had the earthquake and then the subsequent tsunami. 3 others were shut down for refueling, and 1 was shut down, Unit 4, for maintenance. They were replacing an internal component. So I want to show you this picture. And I'll show you this one again before I show you what the site looks like today. You know, it was a beautiful area, very scenic, and they used the ocean as their heat sink for condensing their steam back into to a liquid. The first thing that happened, obviously, was the earthquake, and it was a very big earthquake. If you look at the plant design at 8.2, they had a 9 earthquake, and that is 8 times stronger, so it's a logarithmic scale. So when you think about the reactor having to withstand 8 times greater earthquake than it was designed for. And it turns out that it did fine for the earthquake. From what we know today, the earthquake caused little damage to the plant itself. Now, it did take out their off-site power, and I'll talk a little bit about that. But the plant itself withstood that 8 times greater magnitude of earthquake than it had been expected to encounter. So after the earthquake, the diesel generators started up like they should have. They ran for about 40 minutes, and then the tsunami came, and I'll show you some pictures of that. The tsunami is just incredible when you look at the force of the tsunami and the destruction that occurred. And there's a whole bunch of pictures that I had received of villages along that east coast that showed you basically the village before the tsunami and the village after the tsunami. In a lot of cases, complete villages were just wiped out. I mean, just gone. The force and the destruction was just stunning. There were about 20,000 people that died from the earthquake and the tsunami. And you look at the forces of that water coming through, and a lot of the films that had occurred that showed that, This lower left-hand picture was a chemical plant that burned for 3 days, killed 11 people. But most of the attention was focused on the nuclear plant, even though no one died from the radiation. And from what we know today, there will not likely be any radiation deaths from that accident. I think the biggest traumatic experience that community is going to face is having to be evacuated. So if you look at generations of families living in this area and having to quickly leave, it is very eerie when you drive from Fukushima Daini to Fukushima Daiichi, and you'll go through these villages and it looked like a spaceship came over and just sucked people out. You know, backhoes were working and you tell they were just stopped in activity. You'll see curtains on homes. You'll see plants still in windows. For them to still be alive, they're probably fake plants anyway, but basically you'll see these villages where, you know, just people had to very quickly leave, and I think that will end up being the biggest trauma from that particular event. The wall of water that came in just was stunning when you look at the force. Cars and trucks were just tossed around like they were toys. The force was phenomenal. So this is the actual Fukushima Daiichi plant. And if you look, you'll see that wall of water coming. What I was surprised that those towers stayed up. You know, these are fairly tall towers. And the fact that they withstood the earthquake tells you that they had been overly designed and very robust. But if you look at that wall of water come in, as you look at the coast, as the water gets shallow and this wall of water is coming in, what happened at this particular tsunami, there were a couple of waves that came together that formed the big one. And so they had originally designed that plant for a 3-meter tsunami. They went back about a decade ago and they had determined that, well, they ought to go a little bit higher, and they went up to 6 meters. What actually hit was almost 15 meters. So when you look at that wave coming in, it's actually above the turbine generator building, that wall of water coming in. So you're looking at a wall of water coming in about 50 feet tall. That is a huge wall of water. So when the sirens went off saying a tsunami was coming, the workers really weren't that worried about it because they knew that it was designed, they thought, to withstand the tsunami. But it was definitely underestimated. This is actually a shot at Fukushima Daini, and what happened at this particular plant, it's a little hard to see in the upper right part of that building, but you can see some steam coming out, so that that actually is from their diesel generators were running. But this area was submerged, and I actually walked along that area. The water's gone down, so otherwise I wouldn't have been walking there. But what happened in this particular area, they had the water intakes that were elevated about probably 6 feet off the ground. Well, what happened, the diesels kicked in, but the wall of water that came in was so high, it ran into these the vents that they were sucking in air for the diesel generators. And so all that water rushed down into the generators. If you look at a lot of hospitals, where do you think they put the generators? Put them in the basement. University of Texas Health Science Center in Houston a number of years ago had massive flooding. Diesels were in the basement. They flooded, and they had to basically evacuate the patients by helicopter. This was a case where at the Daini site, the diesels started again like they did Daiichi, but for particularly units 1 and 2, the flooding basically shut them down. So what happened in terms of what nuclear plants do is that in the event when the earthquake occurred, the reactor shut down. And so basically at that point the reaction is shut down, it's stable, but you have to remove about 8% of the decay heat. So the best way to think of that is if you have a gas stove and you turn the flame off and you put your hand above the flame that's now gone, it's not going to be a problem. But if you have an electric stove that's glowing red hot and you turn it off and you slap your hand on top of the burner, you're probably not going to be a happy camper. So that burner has to cool down because it has to remove that heat. Much like the fuel rod, it's hot and it still generates about 8% heat as it decays away in an exponential form. So what happens is that you have basically, if your reactor shuts down, you have off-site power. If you lose off-site power, then you have diesel generators that start up. And so in general, you need 2 diesel generators to remove that decay heat. So you have 3, just in case one doesn't start. In the case of Fukushima Daiichi, the earthquake caused a landslide that took out their off-site power. And so then what happened was diesel generators kicked in like they should have. Then the tsunami came, flooded their diesel generators, but then the next backup system is batteries. So you have batteries that will run for 8 hours. The batteries did not have watertight doors. They flooded. So if you look at losing off-site power, losing your diesel generators, losing your batteries, you're going to melt fuel. You just run the numbers and it's going to melt. So this is what the reactor looked like during construction. And again, it's a boiling water reactor. This is the top part. The containment is actually below the concrete, the gray material. So the containment is below. The containment is not the superstructure above. As the fuel melted, you generated gas. You generated hydrogen. That hydrogen was released, and it blew. And it was, what's interesting about that explosion was the fact that it basically blew the top of that reactor off, but you don't see a lot of burning. It was just a quick release of energy, but it was definitely very destructive. So this is what the reactor site looked like before the accident. This is what it looks like after. If you notice in the next to the water, let's see if I can do this. If you look at these tanks in this area, you'll notice they're gone. So just massive wall of water came in. And so you can see Unit 1, the reactor blew, the hydrogen explosion. Reactor 2, when Reactor 1 blew, it blew the panels off of number 2, so that hydrogen went out and it did not explode. Number 3 exploded, and then hydrogen from Unit 3 came over to Unit 4, which was shut down, and it exploded. So a lot of people thought originally that they had a problem with the spent fuel pool on number 4, but that was from hydrogen from Unit 3. They shared that common stack. So let me show you, I was on the top of spent fuel pool number 4, the one that the top of that building had exploded. And you see these massive walls that just were blown off. They've now removed all of those, and they're getting ready to take the spent fuel out. As I tell everyone, I'm the one that's dressed in white. What they do is when you go into that area, because it's contaminated, you put in double white suits and breathing apparatus. And so when you come out of the hot zone, you peel one layer off, and then you keep the other one. And then when you go out to the clean area, you take it off. So you had double protection. I was underneath the spent fuel pool for number 4 because the perception was that it was leaking, and so I was underneath it, and the integrity was maintained. I'd like to show you this picture. Can you see that car that's wedged between the building? That's 20 feet off the ground. So that car was washed up and went down as the water came down. And so just the amount of destruction was phenomenal. One of the generators for Unit 5 stayed up and running, and the reason it was air-cooled as opposed to water-cooled. And so they did maintain cooling for units. They cross-tied Units 5 and 6, which were both shut down. So those units are okay. So what's likely to happen from Fukushima? There's going to be a lot more focus on station blackout. The United States had already looked at that. Why do you think we looked at station blackout in the past? The NRC spent a lot of effort. 9/11. So after 9/11, the fact that the planes came in, the concern was, would a plane hit a nuclear site, take out your off-site, take out the generators, and then you'd be on battery. So the NRC had required the utilities to do a lot of protection activities. A lot of it is classified. We don't say what those protections are for obvious reasons. So we in the U.S. had already covered that fairly well, but it will go back and look at it again. We'll also look at the spent fuel pool. Even though they've done that for 9/11, they looked at all ways to get water, keeping over the spent fuel pool. The other thing that will occur is here you had basically 4 reactors, only 3 running, but you had multiple reactors that had a problem. In general, the NRC and the industry had looked at multiple reactor sites only having a problem with 1 reactor. They're now going to go back and say, well, okay, well, what happens if we have both of them? Or in case of you have 4 at a site, what happens if all 4 have a problem? New plants, United States, basically natural gas took those out before the Fukushima. So there's really very little impact from the United States in terms of building new plants. Natural gas had already taken them out economically. Germany and Italy, it's interesting that a reactor accident in the east causes reactors in the west to shut down. But Germany made a political decision before they knew all the facts. Merkel knew that she needed the Greens to keep their country together politically for her power, and so they shut down. Italy was thinking about building plants. They decided not to. China probably for about 2 weeks said we're going to pause, and then after 2 weeks they said we have no choice, we're going to go. India also has to look at their entire energy portfolio. They're going to continue. United Arab Emirates, as I said earlier, they're building 4. They're looking at another 4 after the first 4 are going. Questions? I assume there's a magic microphone somewhere. And if they're hard, I'll let Varun answer them.
Thanks very much for the talk. Curious as to why in the hours or days after the accident, why couldn't they bring in mobile diesel generators, to set them up and wire them up? Was all the infrastructure too damaged to connect, mobile units? The
answer is yes. They actually did bring in multiple generators. When I went to bed that night, I stayed up looking at the latest activities, and they brought in 3 portable generators. I thought that they would have had them hooked up, and then the next morning I was stunned when I saw that it had blown. The substations were totally wiped out. They couldn't get into the roads. They had, when I was there, I saw this huge crane. If any of you have seen mobile cranes, you'll see where they have tons of material on the back for counterbalance. This crane was moved 100 yards, just picked up and moved. And so the destruction, they couldn't get things in. The infrastructure was damaged. I can tell you, I went to Daiichi, and then I went to the west coast of Japan where Kashiwazaki, Korea is. They now are putting in huge seawalls. They're putting water tanks, building a big lake high, so unless you have a loss of gravity accident, they'll get the water down. They're looking at, they have a whole bunch of diesel generators that are portable, and they have massive equipment that will move debris out so they can get equipment in. So if they would have done all of those things, Daiichi never would have happened. So, but you're right, the destruction kept those portables out.
Yeah, thanks again for the talk. Post-Fukushima, do you think that there's any reason that the U.S. should have or should look at PriceAnderson again rather than having it extended through 2025?
I think PriceAnderson will get extended. PriceAnderson basically caps the liability of a company. When the U.S. was looking at a diversified energy portfolio, no company wanted to bet their entire company on building a reactor and handling a massive accident like that. And so if you look at things like Sandy, the Hurricane Sandy, you look at hurricanes we've had in Texas, at some point in time the government has to step in. Private industry just can't cover those massive things. So PriceAnderson was a way in which the government actually makes money on PriceAnderson, by the way. So far they've collected a lot more income than they've ever paid out. But if you look at the case of TEPCO, Japan did not have a PriceAnderson where their liability was capped, and then from there the government took over. So the government of Japan has taken over, but they took 51% of TEPCO. So they, in fact, are doing a PriceAnderson, but it would have been much cleaner if they would have had a PriceAnderson in Japan, that concept. So it was clear what the company's liability, where it stopped, and then government came in. It's not clean.
Yeah, I have a question about the possibility of, and again, I don't know where this is, which is why I'm asking you, the prefabricated sort of kind of off-the-shelf.
Small modular reactors.
Thank you. if interest in that is totally waned as a result of Fukushima, or if there is some chance that that actually might be a reality, if not in the U.S. and other parts of the world.
Yeah, the small modular reactors are concepts where you build them in a factory, ship them to the site, and then you have minimal construction. Obviously, we do it with airplanes. We do it with a turbine generator. So big components that are made in factories and shipped to the site, there's more predictability, more quality, more dependability. So when I was at the NRC, I would get about a request, it seemed like once a month, of what I would call a paper reactor. So somebody would sketch on the back of a piece of paper, here's my small modular reactor for the week. And there has to be a lot of detailed design that goes into that. And so the one that I think is going to work is by Babcock & Wilcox. It's called M-Power. It's about 125 megawatts electric. And so the intent is to make them in a 4-pack. Now for college students it should have been a 6-pack, but they're going to make them in a 4-pack. And basically have 2 units per generator. And the concept is to build them in a factory, ship them to the site, so that you don't have a $7 billion outlay. And so you can generate electricity with one while you're building the next one and the next one. And so it's not clear to me how those economics are going to work, but the Department of Energy just announced a week ago they picked Babcock & Wilcox as their one reactor that they're going to go forward with. They're going to do a cost share, and TVA, Tennessee Valley Authority, the old Clinch River site is the site that they're looking at. So it's not clear to me how those economics are going to work out. John Fees used to be the president of Babcock & Wilcox, and I asked him a very simple question. I said, if you look at basically a modular reactor like M-Power, for it to be equivalent to an AP1000, you need 10 of them. So I said, tell me how much concrete, how much steel, how much copper goes into 10 of your M-Powers compared to one, because I wanted to get a magnitude of just the stuff. How does it compare, to see what the cost differential might be. And either he didn't know or he wouldn't tell me. And so I think the economics aren't sure, but I think there is a need to look at small modular. I think the big key for those small modular reactors are at shutdown coal sites, because you have all the infrastructure there. You've got the land, you've got the power, you've got a workforce, you've got the cooling capacity, the substations. And so as these coal-fired plants shut down, there would be a perfect area for a 300 megawatt type reactor. So, but they're going to have to build them and run them to see how the economics really come out.
Yeah, thank you for being with us. So are those diesel generator backups, are they Chinook liftable with dual rotors? Have they thought about getting it that small where a helicopter can go anywhere? Secondly, can you touch on the cultural aspects you mentioned briefly in Japan, and then contrast it to where we have cultural deficiencies that we have to be self-aware of?
The diesel generators that are in these big plants are about the size of a locomotive engine. So you don't airlift those in easily. What the NRC and the industry were doing, they were staging some big generators in regions, and they're going to now expand that so that, for example, you won't have a spare diesel generator the size of a locomotive at you already have a spare. But the case if you have to bring one in, they'll bring them in a different configuration, probably on a truck, and they'll be closer, so they'll look at the time constant. Can you get one there quick enough? And if you can't, you can bring in a portable one. Once you bring one in, it's important that you're able to actually use it, and so that you have to make sure you have the connections there and so forth. So I think the whole world will look at additional backup systems and more what-ifs. What I find amazing is you look at the concept. You had basically the off-site power. You had backup diesels more than you needed. You had batteries, and all of those failed. And fundamentally, the problem with that, it was a bad site. There was a marker that was at that site put in the year 869 that said, don't build here. Not only did they build there, they dropped the site down 15 feet. So there were, if they looked at the risk assessment and the 10 to the minus 6, once in a million chance, they blew it. They never should have put it at that elevation, at that site. If they would have gone up another 20, 30 feet, not a problem. So a lot of lessons. Culturally, the biggest issue I always worried about as a regulator is complacency. The fact that people get too comfortable, they get too assure that they have covered everything. They have to practice, train, challenge, and think every day what can they do to make it safer. So in the U.S., the nuclear industry is very self-critical, almost to the point of being a masochist, where they basically are so critical because they're striving for excellence. But at the same point, that openness and that communication is what prevents accidents. You want to be able to have, if anybody believes there's a safety issue, they can stop the plant, raise issues with no attribution, no retribution in any way. In Japan, it's a very hierarchical culture, and they're just going to have to break that mold just like they did in manufacturing. But it's going to take time. It's not going to be easy. It's going to be a time. I think the area that's amazing that they did it in the U.S. is the Navy nuclear program. I don't think there's any structure as hierarchical as the military. Having served 5 years at the Pentagon, I learned that it's very top-down. But in the Navy nuclear program, anybody can stop an issue on safety. And so within a very hierarchical structure of the U.S. military, they've broken it. So Japan can do the same thing. I think if Japan can learn from this, much like the United States learned from 3 Mile Island, in 20 years, the Japan safety will be just like their manufacturing quality. No reason they can't, but it's going to be tough.
Hi. My question is about technology change in the nuclear power plants, and specifically, what are the major reasons for the high construction costs that haven't come down quickly, as other new technologies over maybe decades?
The cost for nuclear plants is just a lot of stuff. It's material. When you look at the turbine generators, there was a big efficiency and scale in the electrical generation business where generators and turbines would get bigger, more efficient, and cheaper, per kilowatt hour. But if you look at a massive nuclear plant, they are doing things like modular construction, and they're doing more predictable. So you build modules in a factory and ship them to the site. So they're doing that at the Vogtle and at the Scana site. So there are some construction techniques that have gotten more accurate, quicker, better. Certainly computers have let you design, stage, and do things quicker. But when you look at the containment building around those reactors, they're 4.5 feet thick with rebar that's woven into a mesh. The rebar is the size of a Coke can. So just the amount of material in those plants are massive. So you can do more on construction, you can lower some of the costs, but at the end of the day, it's just material. And so that's why, and a nuclear plant is the opposite of a gas plant. A gas plant you can build quickly, low capital cost, but your fuel cost is 90% of your bus bar cost. On a nuclear plant, they're very capital intensive. You can double the price of uranium and it's a who cares on your electrical costs. So once you get a nuclear plant built, your production costs are pretty well known. So in the United States, the cheapest electricity that almost every utility has, and Doyle Benamy had commented on that when he was here, those nuclear plants that have been in operation for 20 years because they've depreciated out their capital, and so now they're just at a low operation and maintenance cost, and so that will be your lowest cost electrical generation. And so if you look at a company like Southern that's building Vogtle, when you build those plants, you're building them for your great-grandkids. Those plants are likely to run for 100 years. They're licensed for 40 because the Atomic Energy Act only lets you go 40, but when I left the NRC, we had already relicensed 69 of the 104 for another 20 years, and we started a program to see could they run for another 20. It was called Life Beyond 60. That wasn't Dell's age. It was basically, is there life beyond 60 for the nuclear plants? So these plants, capital intensive, but they run for a long time.
It made it sound like the big slowdown in the nuclear world in the U.S. has been a result of low natural gas prices. And I wanted to know if you thought you look 5 years down the road and you see $8, $9 natural gas again, if you don't think that there will be significant headwinds to rebuilding the nuclear industry in the U.S.
I think in 5 years, if the price of natural gas goes up to $8, I think you will see more nuclear plants. And that's on two assumptions. One is that the cost of Vogtle comes in close to on time and on budget, that is predictable. So a lot of companies are sort of waiting to see, can we really rebuild these plants or build the new plants on time, on budget? And so if those plants come in on time, on budget, and if their operating costs are what they expect them to be, then I think you will see some more. I think the difficulty that we have, and I was talking to Varun about this earlier, there's two concepts on utility plants. One is merchant, where you basically build a plant and you take your risk. You charge what the market will bear. If the market is too low, you can lose your company. If the market is high, your shareholders are very happy. So, that's sort of the trade-off. Somehow, I think as a nation, we need to look at a diversified portfolio. There's no perfect source. I can tell you that wind is not even close to being economical. If it wasn't for the production tax credits and for the investment credits on those, wind wouldn't be there today. But we need to learn how we integrate those into the system, much like solar. I think we need to have a lot more solar research. And so at some point in time, the government has a role to look at long-term energy plans and play a role. At some point, it needs to kick it in and let the industry run with it. But somehow on these plants that typically run for 60, 80, maybe 100 years, somehow we need to come up with a scheme. And I don't know I'm not a financial expert, but somehow we need to have a balance so that we don't become too dependent just on one source.
Dr. Klein, thank you for being here. Could you talk a little bit about fuel recycling? It seems like something that France has done really well, and it's enabled them to really proliferate their nuclear industry, something we don't do here, and maybe how we kind of start moving in that direction.
I'm a big fan of recycling. We used to throw away aluminum cans and glass, and now we recycle it. And I think if the United States would look at recycling in an integrated way, we would be recycling in the United States, because your waste package would be smaller, 90% volume reduction. You only deal with the issues you have to deal with, and you have a constant or a consistent waste package. So typically, if you look at what France, with U.S. technology, by the way, U.S. was the one that developed the recycling concept. They get the uranium and plutonium out, and they put that back in for fuel for new reactors or existing reactors. So they get the good stuff out and then throw away the residue. The problem that we've had in the United States is that we want a single discriminator on why we do things. And so we want to do it either, well, if we basically recycle, we wouldn't need 2 waste disposal sites. We can only do it with 1. Well, there's a lot of land in the U.S. We have huge land. So, we can afford 2 sites. We don't have to have just 1. The other aspect is, well, we need to do it to get the uranium and the plutonium out, put back in fuel. New uranium is cheaper than what it costs to do the recycling. So we need to look at a systematic approach, and I think ultimately we will. We are the only major nuclear country that does not recycle. France does it, UK does it, Russia does it, China is going to do it, Japan is going to do it. So we're the only major nuclear country that does not recycle. Microphone is there.
Yeah, I just was thinking about, you talked about how we have enough nuclear material ready to be able to go for 700 years.
In a breeder reactor.
In a breeder reactor. It just got me thinking about the fact that, since we've really been using electricity, we're still finding different ways to move a magnet past a wire. And I was wondering if you saw any potential innovation or change happening in the basic ways we produce electricity, in a commercially viable way.
That's a great question. Being into research, I keep waiting for this magic thing to happen, but physics keeps getting in the way. And so I think for what we know today, we've been talking about fusion for decades. And Hans Mark, a former chancellor of UT System, worked in fusion in the 50s. And he said in those days they were saying they would have commercial fusion by the end of the decade. They're still saying it, even though decades keep changing. So, we keep waiting for that magic thing. I think for our lifetimes, I think we're going to have the basic electricity where you generate it. There may be some new form. Star Trek might have those new engines that go faster than the speed of light and things of that nature, and warp speed. But I think for our, certainly for my lifetime, we're going to have basic electricity, and probably for yours as well. there may be something there, but at this point, we just haven't seen it. One more question?
Take one more question here. So can you pass the microphone? Oh, it's there? Why don't you ask your question? We'll come back.
All right, so going back to the natural gas topic, you mentioned that a lot of plants were canceled or deferred due to the low prices of gas. Is there any reason in particular, like the 5 that are still being built, managed to stay economical? Any like specific features or anything?
Yeah, the reason the ones that are being built are economical today is that they did construction work in progress, so that as they build a plant, it goes into the rate base. So if you were to build a house, and every time the materials came, you paid cash, your total payments would be a lot less than when you borrow the money for the house after it's built and then pay it off in 30, 40-year time period. So both in South Carolina and in Georgia and in the state of Florida as well, the public utilities still being regulated, they passed a law that said they'll do construction work in progress. So as they build it, they pay for it. So that keeps the costs down low. So that was one. The other Southern company had applied for a loan guarantee from the government. Still haven't gotten it, but because the Department of Energy and Southern haven't come to terms. But what the utilities want to do is they want to borrow money at the same rate for a nuclear plant that they would for a gas plant. So if you go to your friendly Wall Street banker and you want to borrow a few $1 billion and you say, well, I want to build a gas plant, they'll loan you the money at a certain rate. If it's a nuke plant, it's shot up because of all the uncertainty in that mean old Nuclear Regulatory Commission that might not let you run it. So all of those risks are higher on a nuclear plant, so they charge more. So for a regulated state that allows construction work in progress, looking at energy diversity, nuke plants are a long-term investment. And so I'm a fan of nuclear. It's not the only option, but I think it needs to be a part of our energy mix. But for that to occur, there has to be the economic structure to let a company provide that in a reasonable way, like construction work in progress, and by a guaranteed return on your investment once you build it, so you don't have to guess whether you're going to have $2 gas or $14 gas.
Final question.
Thanks for coming. My question is what's the extent that geography plays in government's decisions to invest in nuclear and where? I mean, it makes sense in France and Germany of, low susceptibility to environmental disaster to have more nuclear plants, but in, the West Coast or California or Japan that are more prone to earthquakes and hurricanes or whatever. We saw at Fukushima that they thought that they had the high enough walls to prevent a tsunami, and they miscalculated horribly. So are the safeguards in place, or do you think geography should play a larger role in that? Geography
always plays a role. So anytime you go as a recovering regulator, I can assure you that whenever a utility would come in and do a site, we looked at earthquakes, we looked at tsunamis. So for example, you don't have to worry about tsunamis in the middle of the U.S., but you have to be worried about earthquakes, you have to be worried about dam failures, you have to be worried about hurricanes, tornadoes. So all of those environmental issues, every nuclear plant in the world has to go through a licensing phase. In the case of Fukushima, they just blew it. Now in the case for, I think the risks of any kind of a traumatic natural environment is no different in the U.S. than it is in Europe, anywhere. Now, in the Pacific area, we know earthquakes are higher. We are re-examining always whether or not the earthquake designs are high enough. For example, you might have heard in Virginia they had an earthquake that exceeded the design expectations. So the U.S. Geological Survey routinely does a calculation of what they think the magnitude of that earthquake is. If that earthquake magnitude goes up, I can assure you the NRC will require the utilities to meet the new requirements for earthquakes, and that would be pipe hangers in general, that the pipes can hang and go through the vibration. Other kinds of things that are already there, like the containment is so strong that it's not likely. So if the resistance to earthquakes goes up, then the NRC and the utilities will have to make modifications to keep it within the 1 in a million chance. So that will always be there. So no matter where that reactor is located, the regulator in that country will have to do a site assessment. In the case of Daiichi, it was just unfortunate. And in terms of the only areas that we had to look at for both tsunami and earthquakes is on the West Coast. In both San Onofre, south of Los Angeles, Diablo Canyon, south of San Francisco, both of those have gone through rigorous assessments of earthquakes and tsunamis. Well, thank you very much.